This video is going to talk about modeling the energy transformations through some different interactions. This assumes that you've already watched the video where I've outlined the 7 different types of energy. If you haven't done that yet, it's called basic energy storage. I would take a look at that first so you can figure out what maybe a little more detail what these types of energy or storage places are that we'll be using through the examples today. I have several different examples. Some of these have been on a worksheet, which are also on Canvas, right? And for those, I've given you the answers. They don't really have the explanations to go with them, but I do expect you to, and it would be nice if you take a look at those. If this is confusing to you, between that and this video, hopefully that will help. If not, just always ask me questions in class. So our modeling we're going to use are called energy pie charts. And for this to make sense, we have to make sure we know all of the objects involved throughout this interaction. So we need to know all of the objects that store this energy in one form or another so that all of the energy can be accounted for. So the first thing I'm going to do with all of these examples is look at what the system is. And that's going to be one of the main priorities we're going to start picking up on in class, is not only where are the energy storage, where is the energy storage changing as these interactions are happening, but what are really all of the objects involved. So for this example, we're picking up a ball and dropping it and letting it come completely to a stop on the table. So if I'm going to look at the system, in other words, what are all of the objects involved throughout this interaction, we need to have a person, because something or someone needs to pick up the ball and then drop it, right? There's the earth, because once it is dropped, it is the earth that makes the ball fall. Now, we really can't say gravity. Gravity is not an object. Gravity is the interaction between the objects, and the objects would be the earth and the ball. So definitely we need the ball also, because the ball is what's being lifted by the person, and then the ball is what gravity is acting upon. And then if it's going to stop on the table, we also need the table, because there's an interaction between the ball and the table. So once again, our definition of energy at the beginning, I said, depends upon something that can change. Definitely the things that are going to change the behavior of the ball of the person, because the person picks it up. The earth is what's going to change its velocity, change its speed on the way down, and then the table is going to change the speed of the ball once they collide. So with the ball being kind of the main object, the rest of these objects are definitely involved in the interaction. All right, so let's take a look and see what's going on. So to begin with, if the person has not yet picked it up, if this ball is on the table, so we want to label kind of the different parts of this thing that could be going on. All of the energy is in the person, and a person has chemical energy, right, in all the cells of their body. I'm sitting there, I have all this chemical energy in my body waiting to pick up the ball, and I get the signal from my brain, pick up the ball, so that I do, right? So when the ball has been picked up and it is at the top of where I'm going to drop it, right, I'm still alive, so I still have my chemical energy, and realistically, I have not used much of my chemical energy to pick up the ball, but just so we have a reasonable amount to talk about, I'm going to say the energy has flowed out of my body and into the ball, and since it is picked up, that is what we call this gravitationally stored energy. So I still have the chemically stored energy in my body, in fact, probably a significantly larger chunk that I put here, but we're going to do that. We're going to say there's this much of the gravitationally stored energy, just so we said we have kind of an area to talk about. After I've dropped the ball and everything else, I'm just standing and watching. So really the amount of chemical energy in my body is not going to change. So this outside area is going to stay the same for the rest of these diagrams. And we could choose several different places to diagram out where the energy is stored for the rest of this interaction. But let's say I want to pick one where the ball has been halfway down. So it is dropped and it is now halfway down. Well, now that it is halfway down, as I said, I'm going to try to draw this about the same, right? This is the chemical energy that's still in my body, but the energy storage has changed inside of the ball. It was all stored as gravitationally stored energy, but now that it's halfway down, half of that is still gravitationally stored, and the other half will be kinetic. Okay, now there's several other places we could do. Let's just say I want to take the first bounce, right? So it is bouncing off the table. It has fallen all the way. It is sitting on the table. It is kind of squashed down a little bit. It's stopped moving and it's ready to bounce back up. At that point, All right, I still have this chemical energy because I'm still watching. And when things bounce, right, because of that elastic energy, so it really is kinetic, all kinetic energy right before it hits the table. That kinetic energy goes into elastic energy as the ball flexes to bounce. And then that elastic energy comes back as kinetic energy as the ball takes off and comes back up in the air. That whole flexing thing causes some thermal. And this thermal energy storage we're going to black out, because once this thermal energy goes into making the molecules move faster inside of an object, we really can't use that thermal energy and store it somewhere else. It's going to stay in thermal. And as I said, then as the ball is flexing and getting ready to bounce, the rest of that would be elastic. So that should be E, EL. And finally, after it's all stopped, the reason it is stopped is because now all of this energy storage is now stored as thermal. And if this is our system, right, to begin with, it is all stored inside of the ball. We are going to look later at what happens to that thermal energy, and we'll find out it actually does not stay in the system. It goes somewhere else. But we will get to that. All right, there's a couple of other examples that I want to show you. And let me put those up here. So the top one has a cart which is already initially moving, and then it's still moving, and these lines are kind of cartoon lines, right? And they show you how fast the the object is moving. In this case, it looks like it is slowed down somewhat, and then the final thing, it has hit a spring and compressed it, and it is not moving at all. Right? For this one and also for the bottom one, I'm not making myself part of the system. So in this, the system would be the cart. Oh, and wouldn't you know it, just about that time, my pen decides to stop writing. So I apologize. Okay, we get red pen for the next little bit here. So this is a cart, and I'll call it a table. I don't really know what it is. And then we also have a spring. Now in discussions in class, people say, wait a minute, you need the earth, right? Because without the earth, the cart wouldn't stay on the table. If there was a change in what was going on, if the earth was causing a change, I would definitely put it there. I mean, the cart is definitely changing as it's moving. If it is changing and it's slowing down, right, it has to be because the table is interacting with it, and definitely it stops at the end because the spring is interacting with it. So you're right, the earth is there, but it's not really interacting to make a change with the cart. And what we're really looking at with energy again is what is changing in the interaction. If you're lifting something up or down, definitely the earth is going to have a change with that because it changes the gravitationally stored energy. But in this case, we're going to leave it off because the gravitationally stored energy is not really changing. I did forget. I was going to make sure I told you on the, when I went through my last video that we do need to say where the gravitationally stored energy is 0 in some of these examples. And if I would set that right at this point, right, once again, that is not changing because it's not changing up or down. Okay, so we'll get more to that in the next problem. So initially, once again, if I've taken the person out of the situation, it is not part of the system. All of the energy in the system is kinetically stored energy because this object is moving. Once again, there are formulas, and we'll get to those. So if this thing is slowed down, it definitely does not have as much kinetic energy as it had. Once again, I don't know exactly how much it may or may not have, but let's just say, at this point it has that much kinetically stored energy. It's less because the thing is slowed down. The question is, what happened to the rest of it? And if there is really no other place for this energy, that this energy could have gone or should have gone, right? Sometimes the energy that is hardest to track is thermal energy. And there really is nowhere else this energy could have gone, so it has gone to thermal energy. At the end, right, when it is moving, there is no kinetic energy, or excuse me, when it is stopped, it is not moving, so there's no kinetic energy at all. It has pushed in on a spring, but if we lost some of this kinetically stored energy that transferred into thermal, lost is a bad word, transferred into thermal here, we should have transferred some more there, so I'm going to assume now that maybe half of it has become thermally stored energy. And the others would be elastic because we have pushed in on an elastic object, on a spring. We've made a spring flex in and compress, and so that energy should be elastically stored energy. So that would probably be a pretty good kind of energy flow diagram or set of these energy pie charts to show where the energy has gone throughout this interaction. Okay, the last one for right now. Right, there are more of these that we did in a lab, right, with some of the toys. As I said, there's the worksheet online where there's some more examples still. If this is not enough examples so that you feel like you're comfortable with this, by all means talk to me, and maybe I'll put together another video with a few more examples. This is one where an object is definitely moving up in the air, which means, yeah, absolutely the gravitationally stored energy is going to change. So once again, we need to put a 0 point for that. And it can be anywhere. I'm going to choose to put it right on the ground, or the floor, or whatever that level is down there. Depending upon where you decide to put the 0 point for this gravitationally stored energy, it is going to change our diagrams. If this is going to be diagram A, and B, and C, right, if I put the 0 for the gravitationally stored energy right at point A, there would not be any gravitationally stored energy here. But if I put it down here, since it is off of the floor or the ground or whatever at this point, there is some, absolutely. Right. Now, the description for this isn't up here, but what this would say is an object is thrown upward and travels from A to B to C. Well, if it's thrown upward at A, it is going to be going the fastest. Right. It's going to be slowing down as it moves upward. It is still moving at B. C, it looks like it has stopped and is ready to come back down again. You should always maybe write yourself some little descriptions beside these so that you can kind of track how this energy is moving. In fact, if we were going to put some velocity, arrows on this, there it's going to be moving really quickly, there not quite so much, and at the top, the speed is 0. I mean, write yourself some notes you can help keep track of what's going on. That would always be helpful. So down at the bottom of this, right, there is a lot of kinetic energy, and maybe just a little bit of gravitationally stored, because there is some, because it is not laying on the ground. Sorry, that's supposed to be a G, right? But it is moving really quickly. Right, at point B, it's kind of in reverse. It is still moving just a little bit. You might make that a little bit bigger, but it is quite high. So it's going to have a lot of gravitationally stored energy. So a lot of this kinetically stored energy has flowed into gravitationally stored energy, but there's still a little bit of the kinetically stored energy left because it is still moving just a little bit. Now, this is a different example than the one up above. Right? This is moving through the air, and when things move through the air at kind of a normal rate of speed, there is some energy lost to thermal, absolutely. So if you wanted to put a small amount here, you could. It would not really realistically be a very big chunk. It would definitely not be something like this. Right? When there's a lot of friction, evidently this must be a really rough surface, or the wheels on the cart are really rusty or something. Right? If it slows down a lot, which this kind of looks like from this diagram it does, there will be a lot of energy that flows into thermal storage. But with things, I said, normal speed moving through the air, not quite so much. When we get to C, there is no kinetic left at all. All of the kinetic energy has flowed into gravitational energy. And once again, if you wanted to put a little thermal energy, I would not necessarily say that's wrong. But once again, it would not be a very large piece of that. This would maybe be just slightly more than this because it's moved slightly further, and then that would be it. So I would think actually having it all be gravitationally stored would not be incorrect. But once again, not knowing if you wanted to put just a little bit of the energy that has flowed from the kinetic into thermal, that would not be the worst way of looking at it either. So those are some examples. As I said, if this still doesn't make sense, by all means take a look at the worked examples on Canvas and ask some questions in class. Thanks for watching.